Hi guys, so today I will actually teach you about Maxwell Boltzmann distribution curve and the rate of reaction. So when we have any reaction, the reactants they will have energy, and Maxwell Boltzmann distribution curve shows the distribution of energy of all these particles in this sample in the form of graph. So if we look at the graph looks like something like this. So I will draw for you. So the y-axis is going to be number of molecules. The x-axis is going to be the energy. So the graph will be starting from zero. Yeah. So it's going to actually will have this kind of shape, and then it will be something like this. Okay, so you can see that it is going to be more inclined to the right hand side. Okay, it's going to be skewed to the right hand side. If you want, you can actually further make it further like this. Okay, but you do not need to actually reach up to zero when it comes to the right hand side. So what does this tell us? This curve tells us. It just simply, if we put it in terms of energy, okay, we can actually say, let's say if this is going to be 20 kilojoule of energy. So if you just bring it up here, so imagine here, I just give you a random number. Maybe this is going to be 5. Okay, imagine 5 molecules having 20 kilojoule in this sample. And then as you move up, let's say this is going to be 30 kilojoule, you can see that probably around 10 molecules, okay, having the energy of 30 and so on. So what is going to be represented over here, the peak over here? The peak is basically to tell us this is going to be the most probable energy. Okay, the most probable energy or the mean energy. So you can see that probably around, if I put it over here, maybe this is going to be around 60. Okay, so imagine this is going to be 60 kilojoule, and there are, let's say for example, 15 molecules having 60 kilojoule. Okay, so let's make it better. So 15 having 60 kilojoule. And as we move on, okay, when we move to the higher energy, there are the number of particles or molecules having higher energy will be less. Like for example, if we reach over here, maybe this one is 150, okay, 150, and you can see the number of particles is going to be less than 5. Okay, so if I just, so maybe I'll just put 2, and the higher than that will be maybe 1, and so on. So this is going to actually tell us that the graph is going to tell us that the particles, they have a certain mean energy, and the most probable energy is going to be represented somewhere near to the, not to the middle, somewhere near to the left, okay, over here. And we can actually tell that when you have more energy, the number of particles are going to be less and less. Okay. Um, so we can actually use this Maxwell Boltzmann's distribution curve to show temperature, okay, the effect of temperature towards rate of reaction, the effect of catalyst towards rate of reaction. So if, let's say, if I want to show the effect of temperature, for example, if let's say I want to draw a graph, okay, to show the how higher temperature, let's say this is the one that I simply drew just now. Let's say the temperature was 40 degrees Celsius. And now I want to draw a graph that is going to be maybe at 50 degrees Celsius. So how am I going to draw that graph? Okay, that graph will look like this. So I will use the red pen over here. So it will start again from 0, and then it will remain, the mean or the peak, okay, will be lower than the original peak earlier, and it's going to be to the right. Okay, you can see This was the original peak, and then now the peak is going to be towards the right. So here, after that, you just bring it in, and then you just keep on going like that. Okay. So this is going to be temperature, okay, which is going to be more than 40. So let's say here, this is going to be temperature 50 degrees Celsius. So what can I say about this new temperature? Okay, the distribution, and then the what can I say about the energy of the particles? We obviously can say that, okay, the most probable energy earlier was 60, but now the most probable energy is no longer 60, it's going to be more than 60. This is evident because I think when you have more higher temperature, okay, there will be more particles. Uh, Generally, the particles will gain energy, and they will actually generally, most of them, they have higher energy. So that's going to be your mean energy, which is going to be more than 60. Okay. And what else? Generally, we can say that the graph is going to be more to the skewed more towards the right hand side, because this is simply because the area of the curve, okay, for both graphs, the area of the curve is going to tell us the total number of molecules in the system. So in order to match up to that, okay, we need to actually, as I think, when you are trying to increase the energy level, the graph will tend to actually become uh, the peak is going to be shorter, and it's going to be skewed to the right. So if, let's say, if I want to draw another graph and it's going to be 60 degrees Celsius, so how I will draw, it will be something like this. And then I will draw like that. Okay, so this is going to be what we how we show, okay, the temperature. Okay, basically the temperature, the more temperature, so the graph is going to be slightly shorter and then skewed to the right. Okay, so simply by telling that the most probable energy is going to be increased, and then this energy are equally they are distributed, okay, with all the particles, and the area under the graph or the curve is going to show the total number of molecules. That's why the shape don't remain the same. They are going to actually be flattened a bit. Now, so that is going to be the temperature. So how when it comes to, let's say, when it comes to activation energy, how do we actually use temperature, okay, to show or the graph to show rate of the reaction? So to show that, okay, so I will actually erase this graph, okay, and we will actually utilize these two graphs, the yellow graph and the red graph over here. So I'll erase the some of the data here. Okay, let me draw again. So this one, imagine this is going to be temperature is going to be 40 degrees Celsius. This is going to be temperature is going to be 50 degrees Celsius. So each of them, okay, we know that activation energy is the minimum energy, energy that is required for the reaction to happen, okay, for successful collision to happen. So imagine this is going to be the activation energy, okay. So this is going to be, let's say this is 90 kilojoule. Okay, now at temperature 40, okay, for the yellow graph, okay, we can actually I'll just draw, these are the total number of particles that has, okay, that has the enough energy or sufficient energy for successful collision. But when you increase the temperature 10 degrees, okay, what happens is the number of particles, the activation energy is still 90. Okay, so when we actually bring this up, what happens is the area under the graph is going to be all this. It means both. Okay, both combination of pink and yellow. So we can see that, okay, the area under the graph for the red graph is going to actually tell us that the proportion of the particles that has activation energy or enough sufficient energy for successful collision is actually a lot. And to be exact, they have found out that increase by 10 degrees Celsius actually doubles the proportion of the particles, and which is going to double the rate of reaction. So anyway, we can actually see that the proportion of the particles having greater than activation energy is more. So we know that the rate of reaction depends, okay, on the frequency of collision. So frequency of collision, generally when you increase the temperature, they will actually collide more. Okay, so frequency of collision generally increases. So 40 to 50, yeah, 50 will have more collision. And we can see the proportion of the particles greater than the activation energy is more. So we have these two recipes for rate of reaction, and for temperature, it actually matches these two recipes over here. So frequency of collision is static, and then proportion of particles greater than activation energy thick. So therefore, okay, if you have a higher temperature, generally we are going to have more successful collision. That will actually increase the rate of reaction. Okay, that is going to be related to temperature. So how do we apply this? Okay, when it comes to catalyst then. Now for catalyst, okay, the graph, we do not need to draw two graphs. That one graph is enough. So if I draw this graph, okay, let me actually change the graph. Okay, so if I draw this graph, okay, I know that, okay, this is, let's say at around here, this is your activation energy. Okay, and then if I want to actually have successful collision, so generally these are the proportion of particles that will have enough energy for successful collision. So what catalyst will do, okay, catalyst is generally we are going to add catalyst to uh, increase the rate of reaction by providing an alternative pathway with lower activation energy. So the term is lower activation energy. So we are going to decrease the activation energy. So this is going to be higher activation energy, okay, based on this energy over here. So the lower activation energy, so there will be a new activation energy. So this one I put C. This is catalyzed activation energy. And if you look over there, okay, if we look at the proportion of particles, okay, having that energy, more than that energy, is going to be this yellow part, okay, plus this part. So now you have 1 plus 2. These are going to be the proportion of particles that has more activation, more energy for successful collision is more than previously, which is going to be just the pink part alone. Now you have more. So generally, this will increase the rate of reaction, because according to the recipe of rate of reaction, frequency of collision should be more. Okay, so here you will have more particles, okay, having more energy. So in this case, not so much on the frequency of collision, but more towards the proportion of particles having greater than activation energy is there. So once you actually have that, okay, that actually tells us that, okay, this is going to have more successful collision, and this reaction is going to happen at faster rate. So this is how we are going to use Maxwell Boltzmann's distribution graph to show on the rate of reaction, how it affects the rate of reaction. This one I have mentioned about temperature catalyst, okay, temperature and catalyst, and how we use the Maxwell Boltzmann's curve for this. Okay, with that, thank you guys. See you. Bye.